Welcome to today's lesson. I'm Semasaka Kirendez. And so today I'm going to take you through a lesson on in physics, and basically we'll look at mass and weight. And straight away we go into the lesson for today. And so today, basically we are looking at mass. We'll look at actually mass. So this is what we're looking at. Mass is actually the quantity of matter or the number of molecules in an object. So when we are talking of mass, we are looking at the quantity of matter contained actually in that body, and that in terms of molecules, defining it in terms of molecules, we are looking at actually the number of molecules contained in that object. And so it is actually a measure of inertia. I would say that it's a measure of inertia. And actually inertia is the tendency of an object, actually for the object to remain. Okay, so it's the tendency of an object to remain at rest. So if you say an object remains at rest, or it continues in motion, it continues moving with the actually unchanged velocity. And so that's what mass is. And so we measure actually mass. Mass can be measured in kilograms. Actually, these are the international standard units for measuring mass. And the other important to note here is that actually mass is a scalar quantity. It's a scalar quantity because it is actually has only the magnitude. Okay, it has only the size, which is actually the magnitude. And also, it's important to note that actually mass remains the same in all the planets, because actually the molecules, whether an object is taken to a different planet, the molecules which are contained in that object will be the same. And the other thing to note is that mass actually is measured using an instrument known as a triple beam balance. I think this is very important because we need to know actually which instrument we can use to measure mass. And the one important thing to note here is that actually mass remains the same. Whether we go to the moon, the mass of the object will be the same. Whether we go to Jupiter, it will remain the same, because it's the quantity of actually matter, so which will not reduce. And so now we look at actually weight. Weight is actually the gravitational force that a planet or a body actually exerts. It exerts actually on that object. In other words, what we are saying is that if an object is near the Earth, it will be attracted towards it. So there is a force actually pulling it, which is known as the actually gravitational force. So similarly, in other planets as well, there is gravitational force. And so this gravitational force is different in different planets and in different locations. Even on Earth, the gravitational force that is exerted on a body would be different at different locations. It is actually a force with which the Earth or a body attracts, as I indicated, actually an object. It's important to note that actually weight is measured in newtons with the actually capital N. So this is very important. And so weight is actually it's important that it's a vector quantity because it has direction. You define the magnitude as well as the direction. And so weight is a vector quantity because a vector quantity has both magnitude and direction. It has different values in different planets. So weight on Earth will be different from the weight actually on the moon. The reason is that both the attraction force or the gravitational force will be different in these different places. And so weight is not the same. In a different planet like the moon, the weight would be the same, would be different from the weight on Earth. And so it is used, and we use a spring balance to measure actually weight. So this is the instrument which is actually used to measure weight, which is the spring balance. And so, as we have indicated here, we are saying actually weight is equal to mass multiplied by gravitational field strength. And the units for mass actually for mass is equal to kilograms, while the unit for gravitational field strength, they are newtons per kg. So in other words, we are saying per kg, what would be the force? And then weight itself will be measured in newtons. I think this is very important because we need to know actually in each quantity. So if you are given a quantity or the mass is made, you are given that actually the weight is equal to mass multiplied by gravitational field strength. And so the gravitational field strength here, for example, for on Earth, it is approximately 9.80 newtons per kg. So this is very, very important. And so now we want to apply to equation here. Where, this is the equation. John's mass is actually 8 kg, calculates his weight on Earth, where the gravitational force is 9.8 newtons per kg. So as we indicated, we are saying weight is equal to mass multiplied by the gravitational field strength. And so we are given that actually the mass is 8 kg multiplied by the gravitational field strength on Earth. It is actually 9.8 newtons per kg. And here you notice that actually here this weight here will cancel with it. I mean, this the grams here will cancel these grams, and you are remained with actually the newtons. And so we continue with our calculation. In other words, what we are saying now, we are saying weight multiplied by 9.8 newtons, which gives us actually, which will give us actually 294 newtons. And so this is what we get. Okay, but here, what we need is that what we mean here. So what we meant here, this is 9.8 newtons per kg. And so we have noticed that actually this is the weight that we have calculated, or actually the ball. So the second question reads as follows: what is the mass and the weight of John on the planet where the gravitational force is 1.2 actually newtons per kg? So as we said, the mass does not change. Will not change. So we are saying the mass will not change in every planet because it's a quantity of matter, and therefore it will be the same. It will be actually 30 kg. What about the second question? What will be the weight? The weight would be actually weight, as we indicated, weight is equal to mass multiplied by gravitational field strength. So on this planet, the weight would be 8 kg multiplied by 1.2 newton per kg, because we said that actually the gravitational field strength there is 1.2. Note that here actually this is going to cancel. Kilogram here is going to cancel. So our weight will be equal to actually 80 divided by 1.2, which gives us 80, actually 86 newtons. So this is the weight. And so I thought today we look at actually these few questions and calculate actually weight of objects in different actual planets. And so we can conclude that here the weight is different in different planets, while the mass has remained the same. I thank you.